My worry is that if artificial intelligence is allowed to develop entirely separately from us, and if it develops a lot more quickly than we can alter our biological bodies, then it may become vastly more intelligent, more wise than us, and we'll get left behind. And personally, I don't want to be left behind. I'd rather be up there with the most advanced creatures.
If we don't want to end up obsolete at birth, if we want to stay the most advanced beings, there seems to be only one solution: to become robots ourselves.
Whether we like it or not, we're becoming cyborgs. We're becoming transhumans. Transhuman is an evolution from human to post-human, where we're no longer exclusively biological. So the cyborg is having all sorts of add-ons. Are we walking around naked? No, we have clothes. We have eyeglasses. We have earplugs. Now these are very, very basic, early add-ons to our biology. We're also having much more innumerable add-ons, prosthetic parts, inorganic hearts. We will see much more advanced prosthetics in the years to come. Eventually we'll have entirely prosthetic bodies.
Human as a design is a wonderful design, but humans as a design have some faults. One fault is we were not designed for the modern age. The industrial age has equipment moving faster than we are, and equipment that's very large that crushes us. So we were designed with an endoskeleton, meaning our bones are on the inside, with our soft tissue on the outside. The world would be better for us now if we had our bones on the outside like an exoskeleton. So we were like a beetle.
Post-human, I think, will be post-biological. By that I mean that it'll be a gradual process. There won't be any sudden transition to a different form. I think we'll gradually integrate more and more technology into our bodies. We'll be replacing our organs with more efficient organs. We'll gradually replace this neural tissue because it dies off after a while. It's easily subjected to chemical damage. So eventually I think we'll replace our brain cells with essentially computerized parts. It'll be much more efficient, much more powerful.
To become cyborgs able to compete with the rapid evolution of computers, we first have to understand how our own brains function. The research in this area has boomed in recent years. One of the factors behind this is the development in scanning techniques. They are now at the level that enables us to observe individual nerve cells at work in living animals.
So is this dying out here? Or is that
it's in the process of growing in.
The technique is based on fluorescent jellyfish. Dr. Lichtman isolated the gene responsible for the fluorescence. He implanted it in mice and continued his experiments until he had a mouse of which only the brain cells were fluorescent.
They're genetically engineered so that these are now heritable strains of mice. We have a yellow mouse strain, we have a blue mouse strain, we have a mouse strain where only a few cells are labeled, and we're now generating mice that have multiple colors in them. We call them rainbow mice.
With this technique, we can see individual nerve cells make connections with each other and emit signals.
It's really quite jaw-dropping. It's beautiful when you look inside and see these nerve cells that have always been there, but never easy to see before in living animals.
This technique is used now by many laboratories, helping in their efforts to understand how the brain functions. Other scientists use a completely different approach. They take the brain cells apart and let them grow in a small dish on top of a computer chip. The problem with this technique is that it is extremely difficult to place each cell exactly on the right connection point. A team of researchers at IMEC has recently found the trick. They printed a pattern on the chip with a product that the brain cells love to eat. While consuming the product, the cells get stuck to the right spot and their tentacles are guided by the pattern. This way, the whole network of brain cells can be entirely controlled. Some scientists have already been experimenting with such brain dishes. Their chips were less precise, but their results sometimes remarkable.
Let me disconnect the light show.
Dr. DeMars, for instance, tries to communicate with his brain dishes and teach them several tasks.
So each of these dishes contains about 20,000 or so neurons, which are firing away as we speak. So each one's an individual network, and they'll fire spontaneously. We take living rat neurons, and they will rapidly form a neural network. And we have this grid of electrodes underneath the surface of these living neurons, and we can listen to the conversation among the neurons. And we can also stimulate activity within that network. We can send in different patterns of stimulation and look at how the network changes as a result of those stimulations. And that's how we do what we do.
What he does is to teach his brain dishes how to control an airplane.
The network can essentially fly the aircraft in a pretty optimal way. So it won't overcorrect too much, and it'll be able to stabilize it in a wide variety of conditions. I think I've programmed like a 50-knot crosswind into this one. It was what it looks like. And you can see it, the aircraft, when it hits one of these crosswinds, how it begins to oscillate. The oldest dish that I've had is at 2 years. And the only reason why that dish died was because we were moving the lab from Caltech to Georgia Tech. Otherwise, that dish would probably still be alive today. Each dish has a characteristic, so you can learn to recognize one dish from another dish. They're demanding, though. You have to feed them once a week. And
more and more, we will be able to measure and understand how our brain cells function. Deciphering our consciousness is another question. But the experiments of Dr. Yang Dan have proved that in principle, it is possible to read and to understand the brain.
I didn't know that we started this thing again. So this is a digitized movie. We present this to the animal, and we record the activity of their visual neurons. And these electrical signals that we recorded from will travel through these cables.
She managed to tap the vision from the brain of a cat and to reconstruct what the cat sees onto a computer screen.
So this is a digitized movie. This particular movie is a short clip from Indiana Jones, I think.
Here we see the two images next to each other. On the left, the image that was shown to the cat. At the right, the image that is tapped out of the cat's brain.
The picture has a lot of random flickering, the noise. That's probably the noise of the actual neurons, because they sometimes fire spontaneous spikes. We consider those noise, but maybe they reflect something else, maybe the thoughts or something. But we can distinguish that. So when we use all of those, thinking that they represent visual information, this is the reconstruction that we come up with.
It is the first time an image was tapped from a brain. It proves that we can read and understand the grammar of it. The face is recognizable, but I still can't avoid the impression that the face has something cat-like. Dr. Theodore Berger is head of the Center for Neuroengineering at the University of Southern California. With a team of top scientists from different disciplines such as neurology and computer programming, they have collaborated to develop a chip that can replace parts of the brain, or, on a longer time frame, add more brain power.
One of the first things that we do in this process is to actually study this part of the brain experimentally. We need to know very precisely how it behaves if we're going to reproduce that function in a computer chip and put it back into the brain. So what we do is to take the brains out of the animals that we use for these experiments and then slice up this brain tissue and keep the slices alive in a dish, and we study the electrical properties of these neurons. Neurons happen to use electrical impulses to communicate with each other the same way that transistors do in a circuit. And so essentially what we do is to test the cells to find out, when we give them computer-generated signals of all possible signals, we give them random signals and we ask, how do they behave? And by looking at the translation, we figure out what the function is, and we can describe that function with a set of mathematical equations.
This portion is simulate one neuron.
My colleagues have taken that mathematical model and built a microchip circuit, very small, millimeter by a millimeter. So we can take a part of the hippocampus that's a circuit, we can cut out parts of it, throw it away, and we replace it with the microchip. And so now the whole circuit works just like the biological circuit, so that incoming information looks like, incoming temporal patterns look like outgoing temporal patterns, just like it does for the biological piece of tissue. But now there's a microchip in there, instead of having biology in there.
The chip is presently being tested on animals. One problem that remains is how to connect the chip to the brain. Today's technology uses tiny electrodes, but in the future, another option might be to put some brain cells directly onto the connection points of the chip. They would then be guided to form connections at exact points within the brain in order to establish the perfect interface.
Ça pourra permettre de réparer des cerveaux endommagés à la suite d'accidents, de blessures, n'importe quoi, de maladies. Mais d'un autre côté, ça permettra aussi de faire une communication peut-être directe de cerveau à cerveau. Des choses qui sont effectivement pour l'instant limitées, la communication intra-humaine étant limitée avec la parole, alors que là, l'idée qu'on peut directement peut-être communiquer des expériences globales de cerveau à cerveau, c'est quand même quelque chose de fabuleux qu'on peut rêver. Et puis bon, il y a des tas d'autres applications peut-être plus pratiques à court terme.
One such concrete application has already been realized. The chip is used to recognize sounds, since it can literally do that with the same accuracy as we do.
So we've used these brain-based models as to develop acoustic recognizers. So we train them in the same way that your brain learns to recognize a particular sound. And one of the first sounds that we've developed is one for gunshot recognition. It's a model of how hippocampal neurons communicate with one another. That's all it is, biology.
You got one over there across the park, then they have another one they used to have right there. Then they just put up another one over here 2 days ago. These high-tech cameras, they are called Crime Stoppers. If a gunshot goes off to my left or to my right, the camera automatically traces down the sound of the gunfire and zooms in and takes pictures.
You cannot buy a system today that can recognize speech signals or any other signal in noisy environments. They don't work. But your brain works that way, and because our model is based on the brain, our models work in noisy environments.
And the thing is, there are no cameras installed in the white neighborhood, but we have 5, 6 cameras in the black neighborhood. So the black neighborhood is being watched.
If an airline pilot is about to press the wrong button, it may be important enough to think about trying to identify what the patterns of thought are, what the memory patterns are, and if the person is recalling pressing the button so that we eject right, when they're not supposed to, or press the button so that a bomb goes off and they're not supposed to, then you might want to intervene and prevent that. I'm part of another project that is funded by DARPA that's trying to understand exactly that. I mean, how is information represented in the brain?
And science is supposed to have all the answers. But this has got to work.
It's not going to fail, not after we've come this far. We have here, for all practical purposes, a normal human being, except for his electronic sensory control system, of course.
On devrait, avec des localisations donc de ces circuits électroniques dans différents endroits du cerveau, de pouvoir lire le contenu du cerveau et le mettre sur un disque dur, le transmettre directement sur à une autre personne, etc., etc.
Part of our problem is in getting enough sensors into the brain without destroying it. Getting enough sensors in there so that we can extract enough information to infer what the total pattern of activity is. And if we can do that, then we have to develop a mathematical model of how information along all those pathways develops and is processed. And so for the next few years, that's going to be the task. Now, if we can do that, then we'll get to the finish line. We will get to the finish line.
a conservative statement to say that by 2025 we'd be able to look inside your brain, see everything that's going on, all the interneuronal connections, all the synaptic clefts, all the neurotransmitter strengths, and create a huge database and copy down every salient detail, and then reinstantiate that information in a neural computer of sufficient capacity and create basically a copy of the thinking process that takes place in your brain. Now that's one scenario, but it's really an existence proof to show that we can tap the secrets of intelligence that exist in, let's say, the human brain. Once we've scanned that information, we can also understand it, see how it's organized, improve on it. We can extend it. We can make the memory 1,000 times bigger. We can make it faster. We can expand the perceptual capabilities.
To transfer your mind to a computer, this seems to be the ultimate dream of many scientists. To liberate us from our old body that is becoming obsolete in this technological world. We would then go on living as free spirits in cyberspace.
I'm not interested in a future where there are post-human beings if I'm not one of them. I want to be there. It's very important to me that I live and thrive in the future, not just to think about some robots taking off into space. I want to be there.
So in a way, mind uploading is a shortcut around artificial intelligence that will allow us to have machines with human minds.
I'm hoping that we could fit on a CD-ROM. That's 600 megabytes. And I'll bet that that's all you need to copy a person.
So it's a difficult time to predict what these new humans will be like. I think it's important to include the third component, which is the virtual, along with the artificial and along with the flesh. But how that mixture goes together in a cooperative versus a competitive way is hard to predict. It's very interesting. It's a great time to live in. But I'm anxious to wait 50 years to see what the answer is.
Reality and virtual reality are beginning to merge. To understand how this will occur, we have to look at one more technology slated to overshadow all other branches of technology. It's nanotechnology, the means of getting control over matter, atom by atom.
So what we're going to do is move this atom from this location here to a location right over here. We'll move it just along this path here. Now you got to get excited about that. You just got to get excited about that.
Scientists are now able to grab one single atom and move it to another place. It's a small step for an atom, but a giant leap for mankind. If we start making things by building them atom by atom, we can make almost anything we want.
Manufactured products are made from atoms, and the properties of those products depend on how the atoms are arranged. Now, today's manufacturing technologies arrange atoms very crudely and statistically, but in the future, with nanotechnology, we'll be able to arrange the fundamental building blocks of matter in precisely the patterns we want, very flexibly and very inexpensively.
Nanotechnology will open vast opportunities for all other technologies, in particular for computing. When computer connections can be made by single atoms, computer power will increase enormously.
Computers incredibly powerful that just would let us put into a single sugar cube a computer that was more powerful than all the computers in the world combined today.
But there are many other fields in which nanotechnology will be applied. While at the end of the last millennium, most scientists believed that nanotechnology would remain science fiction, We now see its first applications already appearing on the market.
So we now make materials which purify water, which generate electricity, which generate chemical energy. And our long-term research project is to build a system that processes information, kind of like an artificial neuron. You're going to start seeing systems and processes like that proliferate within the next 45 years, in which you're going to be amazed constantly.
This rotating dot here is the first real nano engine ever made, only a few atoms in size.
I took the F1 ATPase and I stuck a little propeller on the top of it and made it spin around from one molecule. Well, now I can take many thousands of these in complex systems like we have in our bodies and make them do more sophisticated things.
The ultimate goal is to create robots as small as viruses, called nanobots. These nanobots will be more intelligent than today's computers. One possible set of applications is medical. Nanobots could be injected into the bloodstream as a kind of cleansing team to kill cancer cells, for example, or to carry out other kinds of maintenance work in the body, or even to modify the DNA code. It might seem that this is a very expensive technology, but in fact, the opposite is true. We will be able to program nanobots to reproduce themselves, just as all natural creatures do. They will then be able to grab material from their environment and use it for making copies of themselves.
Well, the basic goal of nanotechnology is to build what's called an assembler. And this is simply a very small device that can make copies of itself. And it's a programmable device, so it can be programmed to build a wide range of useful things.
Autoassemblers can be seen as a new form of life, comparable to viruses or yeast cells. They can reproduce themselves, and at the same time transform matter just as yeast cells change sugar into alcohol. The only difference is that these new creatures can be programmed to carry out whatever task we want them to. Change carbon into diamonds, perhaps, or create food.
Molecular nanotechnology is to physical reality what computer programming is to virtual reality. I think that's a bit of an exaggeration, but gives the idea. Whereas computer programmers can program software to do what they want, molecular nanotechnology will allow us to change matter at the most fundamental level. It will allow us to build just about any kind of structure to our exact specifications by moving individual atoms.
This sounds like a world of magic, where all that we imagine becomes reality. But the role of the good fairy is taken over by robots so minuscule that we cannot see them. And instead of saying the magic word, we program them to grant all our wishes. The other side of this fairy tale, however, is what is called the gray goo syndrome. Imagine that some nanobots are programmed for a terrorist action, or would simply tilt and start reproducing themselves endlessly. In a rapid chain reaction, the Earth would be reduced within 72 hours into a gray goo of swarming nanobots. Most scientists, however, stress that such a scenario is very unlikely. We will have nanotechnology to control nanotechnology, and it will also provide the ultimate escape route. We will be able to inject a certain number of nanobots into our bodies, where they will locate our brain cells and copy their functioning. With no effort, we will get a hardware copy of our consciousness that will then send a software copy to a computer, where more copies can be made, or where our consciousness will be allowed to merge with other souls and software programs. Then we will be ready to leave this planet and start the exploration of the universe. What is our place in this magical world where everything can be transformed? How will people deal with such a future? Or is it something that by definition goes beyond our human capacities to understand? Something that only transhumans will be able to grasp? Will we stay as we are and watch with wonder from the sidelines? Or will we upload ourselves and participate in the world as super beings? Let yourself upload to a network of nanocomputers and let the wind carry you.
It's important to recognize that the post-human epoch is coming. It really is. It's what we want, and it's kind of, you can see it written in the pages of magazines. It's the word of the prophet is on the subway walls here. We really, really do want to violate human limits now, and we're getting closer and closer to the ability to do it. But it's also important to realize that this is not the end of history. It doesn't solve any of our other problems. It just creates new problems that are going to intensify. And there's going to be more than one kind of post-humanity. And the mere fact that you're no longer human doesn't mean you don't have the same personality problems that you did before. It doesn't liberate you from yourself. It probably makes you more than you were before, not less. You're not going to clank and beep like RoboCop. You're just going to have new abilities and new powers. And, you know, dealing with power is troublesome. If you have more power, you have more responsibility, not less.
Your playlist shifts to your favorite song, sending chills up your spine as the music begins to play. You glance at the program running in the background on your computer screen and notice a now familiar sight that appears whenever you're overloaded with pleasure. Your theta brainwave activity decreasing in the temporal regions of your brain. You mentally move the cursor to the left and scroll through your brain data over the past few hours. You can see your stress levels rising as the deadline to finish your memo approached, causing a peak in your beta brainwave activity right before an alert popped up, telling you to take a brain break. Your mind starts to wander to the new colleague on your team, whom you know you shouldn't be daydreaming about, given the policy against intra-office romance. But you can't help fantasizing just a little. But then you start to worry that your boss will notice your amorous feelings when she checks your brain activity and shift your attention back to the present. You breathe a sigh of relief when the email she sends you later that day congratulates you on your brain metrics from the past quarter, which have earned you another performance bonus. When you arrive at work the next day, a somber cloud has fallen over the office. Along with emails, text messages, and GPS location data, the government has subpoenaed employees' brainwave data from the past year. They have compelling evidence that one of your coworkers has committed massive wire fraud. Now, they're looking for his co-conspirators. You discover they are looking for synchronized brain activity between your coworker and the people he has been working with. While you know you're innocent of any crime, you've been secretly working with him on a new startup venture. Shaking, you remove your earbuds.
What do you think? Is it a future you're ready for? You may be surprised to learn that it's a future that has already arrived. Everything in that video that you just saw is based on technology that is already here today. Artificial intelligence has enabled advances in decoding brain activity in ways that we never before thought possible. After all, what you think, what you feel, it's all just data. Data that in large patterns can be decoded using artificial intelligence. We're not talking about implanted devices of the future. I'm talking about wearable devices that are like Fitbits for your brain. The newest way to monitor attention is through a device like this one. These are ear pods that are launching later this year. These ear pods, much like the video you watched earlier, are ear pods that can pick up brainwave activity and tell whether or not a person is paying attention or their mind is wandering. Okay, well, you might think, fine, but even if we can tell whether a person is paying attention or their mind is wandering, you can't tell what they're paying attention to. You would be wrong. It turns out that you can not only tell whether a person is paying attention or their mind is wandering, but you can discriminate between the kinds of things that they're paying attention to.
I think the danger of AI is much greater than the danger of nuclear warheads by a lot. Mark my words, AI is far more dangerous than nukes.
I try to convince people to slow down AI, to regulate AI. This was futile. I tried for years.